after we introduced the electric potential, we looked at a case of a surface charge and the electric field at the boundary, basically at the surface, and the electric potential. And what we found was that the electric field was discontinuous, but the electric potential was continuous across the boundary. So we can now think about or start to look into what happens with magnetic fields. And so for that case, we can look at a surface, but we're going to look at a surface current as it flows across the surface, and then take a look at the magnetic field that we have. So I'm just going to draw this surface here, and we have some surface current which is now flowing across this surface. Now the magnetic field should be perpendicular to this surface current, so the possibilities are that I would have a perpendicular magnetic field which is above, so that would be pointing in this direction. I would have a perpendicular magnetic field below, which would be pointing back basically in the same direction. Now, I could have a magnetic field which is tangential below, and I could have a magnetic field which is tangential above. If you think about it, I could also have let's imagine I have a magnetic field which is parallel above and a magnetic field which is parallel below. So basically those are all of the possibilities that I have for magnetic fields created by this surface current. Now if I look at the total flux of the magnetic field across the area, if it's a closed surface, then that should be 0. So the amount of magnetic field entering should be equal to the magnetic field exiting through a closed surface. So that would imply then that perpendicular magnetic field above minus the perpendicular magnetic field below will be equal to 0. Or another way of saying it is that the magnetic field, the perpendicular magnetic field above, is going to be equal to the perpendicular magnetic field below. Okay. Now what about magnetic field that is, say, we're summing the magnetic field along a path. So we can look at a closed path. So in this case, what we have is the parallel component of the magnetic field above minus the parallel component of the magnetic field below times the length should be equal to mu 0 times the enclosed current. And this enclosed current is the current density times the length. Therefore, the parallel magnetic field component above minus the parallel magnetic component below is equal to mu 0 times the current density. So the same should be true for the tangential magnetic fields. So what we get is that the magnetic field component that is parallel above minus the magnetic field component that is parallel that's below it is equal to mu 0. If I want to write this in a vector form now, it's the current density dotted into the area vector, where this area vector is pointing perpendicular to the surface. Okay. So what does this mean? Is, well, if the difference in the magnetic fields is not zero, that means they're not the same. And the differences in these magnetic field components turns out to be the current density. That quantity right here, which is very similar to what we had with the electric field, except the last time I believe it was the perpendicular component, was equal to the, not the volume, but the surface charge density divided by epsilon naught. So nature again gives us these parallels between the discontinuity in the electric field was basically caused by the charge, and the discontinuity in the magnetic field is caused by the currents. But just like in the electric case, the magnetic potential is continuous at the boundary. So the magnetic potential above is going to be equal to the magnetic potential below, because the divergence of the magnetic potential is zero. So basically the change in the potential is zero, therefore there shouldn't be any discontinuity between them. Because the magnetic field is the change in the magnetic potential, basically a spatial change, a change of the magnetic potential over the space, there is this discontinuity, and therefore I can rewrite this equation as the change in the magnetic potential above divided by the area direction, or basically the change with respect to the area direction, minus the change in the magnetic potential below is equal to minus mu zero times the current density. Again, this is very similar to what we had before, which is the change in the electric potential above minus the change in the electric potential below was equal to minus the charge density divided by epsilon naught. And so what happened, the form is essentially the same. The only difference is that in the magnetic case, the potential is a vector, therefore it's equal to its change is equal to a vector, which is the current density. The current has a specific direction to it. With the electric case, the electric potential, its change, is equal to a scalar, basically the amount of charge density that we have. And in both cases, there is this constant of nature, either mu zero or epsilon zero, which are basically giving us the strength of the interaction, and so they are included in this result.